Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today we're going to talk about surface integrals. So far we've discussed one of the three main integral theorems in this chapter, Green's theorem. The limitation for Green's theorem is that Green's theorem only works in the plane, R2. We need to expand that to R3, to spaces. And the remaining two integral theorems, Gauss's divergence theorem and Stokes's theorem, both work in R3, and they both use a concept called surface integrals. Surface integrals use parametrized surfaces. Earlier in this course, we parametrized curves. Now we're going to parametrize surfaces. In general, a parametrized surface is a function phi mapping a domain contained in R2 into R3. Since you have two independent degrees of freedom in the domain, you end up with a two-dimensional object embedded in three-dimensional space. That's called a surface. They will generally have the form uv equals x of uv, y of uv, z of uv. So the x, y, and z coordinates will depend upon the independent parameters u and v. If your surface is of the form z equals some function of x and y, then you can find a much easier parameterization in terms of the parameters x and y, namely x, y, f of x comma y. You can see how x is x, y is y, and z is f of x comma y. These represent points on the surface, just as these represent points on the surface in R3 as well. Just as with curves, there is no one parameterization for a surface. So for example, suppose I'm dealing with the surface z equals x squared plus y squared. Can you identify that kind of surface? That is an elliptic paraboloid. Has rotational symmetry around the z-axis, you realize. One parameterization involves x and y in an obvious way. But instead, you can also convert to cylindrical coordinates and use r and theta as parameters. In this case, x will be r cosine theta, y will be r sine theta. Those are the usual conversions between cylindrical coordinates and rectangular. And since x squared plus y squared is r squared, z will be r squared. This is a rather convenient parameterization for many applications. As another example, if I have x squared plus y squared plus z squared equals 9, that's a sphere of radius 3. I should parameterize this using spherical coordinates. But in this case, the radius, rho, is 3. So my parameters will be phi and theta. I'll have 3 cosine theta sine phi, 3 sine theta sine phi, and 3 cosine phi. You'll remember I asked you to memorize these formulas, the conversion between spherical and rectangular. X is rho cosine theta sine phi, y is rho sine theta sine phi, and z is rho cosine phi. To formulate this parameterization of the sphere, all I had to do is replace rho with 3. As another example, suppose I have the cylinder x squared plus y squared equals 4. X and y are constrained, but z is not. So z will be an independent parameter. Because this cylinder has rotational symmetry around the z-axis, it will have a constant radius, r, of 2, and theta will be a second parameter. So our parameterization will have theta and z as parameters. And it will be, remember the conversion formulas between cylindrical coordinates and rectangular coordinates. R is fixed at 2, so we get 2 cosine theta, 2 sine theta, and the independent parameter z. Parameterizations for quadric surfaces are usually fairly simple. Suppose I have x squared plus y squared minus z squared equals 1. Do you remember what kind of surface that is? That's a hyperboloid of one sheet. The way that we can do this is we can collapse pairs of variables into a single variable in the following way. If I have a sum, say between x squared and y squared, here's what I'll do. I'll set x equal to u cosine theta, y equals u sine theta. With this, x squared plus y squared will be u squared. That will convert the original equation into u squared minus z squared equals 1. At this point, we'll choose the parameterization u equals secant phi, z equals tangent phi, using the Pythagorean identity that secant squared phi minus tangent squared phi equals 1. This, together with this, gives us the parameterization that we seek. The parameters are going to be theta and phi. X is going to be cosine theta secant phi. Y is going to be sine theta secant phi, and z is going to be tangent phi. Oh, but you ask, what if I have x squared minus y squared minus z squared equals 1? A hyperboloid of two sheets. Well, you can write that as x squared minus the quantity, y squared plus z squared equals 1, and collapse the y and z first. That will give you x squared minus u squared equals 1. We'll choose x equals secant phi and u equals tangent phi. And the rest is obvious. To find surface area requires that we first find a surface element. Suppose we have some surface like this, and we would like to find a little area of a patch on the surface, a little element of surface area. We'll take integrals of surface elements in order to find surface areas. These surface elements will depend upon two directions. Here's what we'll do. We'll take our surface parameterization and then we'll find tangent vectors to the surface in the following way. If we hold v constant and take the derivative with respect to u, we'll get a tangent vector, because when we hold v constant and allow u to vary, we end up with a curve on the surface. Taking the derivative then gives us a tangent vector to that curve. We'll call that tangent vector tu. Similarly, holding u constant and allowing v to vary gives us another curve on that surface. Taking the derivative, we'll get a tangent vector tv. Once we have these two tangent vectors, we'll find the area of a little surface patch by doing the following. You'll recall that the area of a parallelogram spanned by two vectors is the norm of their cross product. Our element of surface area will be the norm of tu times du cross tv times dv. We'll perturb an infinitesimal amount in the direction of tu and an infinitesimal amount in the direction of tv. When we take the cross product, we end up with something that has a norm equal to the area of the little parallelogram, infinitesimal parallelogram, on the surface. That gives us the element of surface area. It follows then that the element of surface area is the norm of the tangent vectors tu cross tv times du dv. This works for all parametrized surfaces. Let's do an example where you know the answer. If you have a sphere of radius r, the surface area is 4 pi r squared. A parametrization will be capital Phi of lowercase phi theta equals r cosine theta sine phi r sine theta sine phi r cosine phi. I hope you don't mind if we make the following abbreviations. Instead of writing cosine theta, we'll write c with a subscript of theta. And instead of writing sine phi, we'll write s with a subscript of phi. This will save us a lot of room on the page. R sine theta sine phi and r cosine phi. We'll calculate now the tangent vectors, and it is almost always better if you write the parameters in the order phi theta and calculate t phi first. There's a systematic reason for doing this. The derivative with respect to phi will be r cosine theta cosine phi. The derivative with respect to phi will be r sine theta cosine phi, and then minus r sine phi. Now for the tangent vector t theta. That'll be minus r sine theta sine phi, r cosine theta sine phi, and 0. There are no thetas in the z-coordinate, so its derivative with respect to theta is 0. Now to calculate t phi cross t theta. As you know, the cross product of two tangent vectors will be normal to the surface. In this case, when you take the cross product in the order t phi cross t theta, it ends up pointing out of the surface. This will be important for us later on when we're calculating fluxes, which requires an exterior unit normal. So, calculating the cross product, we get 0 minus a negative, that's r squared cosine theta sine squared phi. We preemptively get a minus on the middle cofactor for our cross products. We'll have 0 minus a negative and a negative How many negatives is that? Negative times negative, that's 2 negatives, and we're subtracting, that's 3 negatives, but then we have the negative on the cofactor. That's 4 negatives. We end up with r squared sine theta sine squared phi. And now this last computation. The norm of t phi cross t theta can be calculated as follows. Note that r squared is a factor on each coordinate. We can factor that out, and scalars come out of norms in absolute value. R squared is already positive. We can also factor out a sine phi. That takes one sine phi from each of the remaining coordinates. That too will come out, since after all phi goes from 0 to pi, first and second quadrants. Sine is positive in those quadrants, so we don't have to worry about an absolute value. We take the square root of the sum of the squares of everything that's left. That's cosine squared theta sine squared phi plus sine squared theta sine squared phi plus cosine squared phi. Now, on the first two terms under the radical, we can factor the sine squared phi out and get cosine squared theta plus sine squared theta. By the Pythagorean identity, that reduces to sine squared phi. Sine squared phi plus cosine squared phi, again by the Pythagorean identity, is 1. So we find that the norm of the cross product is r squared sine phi. That means that the element of surface area is r squared sine phi d theta. Remember, it was ds equals the norm of tu cross tv du dv, where u and v are the parameters. For us, the parameters are phi and theta, so we get d phi d theta. To find the surface area, all we have to do is integrate the surface element over all of the values of the parameters that sweep out the surface. Since we have two differentials, we will have a double integral. The integrand will be the element of surface area and will go over the domain of parameters. In this instance, the surface element is r squared sine phi d theta. Theta will go from 0 to 2 pi, and phi will go from 0 to pi. R is constant, so it can come out of the integral. There are no thetas, so we get 2 pi for free. And the rest is an integral of sine phi from 0 to pi. That's one bump. And one bump gives you 2. And so we've just proved the formula for the area of the sphere. Suppose we have the surface z equals 9 minus x squared minus y squared. An elliptic paraboloid open and down, peaking at a height of 9, intersecting the xy plane at 3. Let's only look at the part for z bigger than or equal to 0, the part above the xy plane, and let's find the surface area. First, we need a parametrization for this surface. Probably better, since we have rotational symmetry around the z-axis, to use cylindrical coordinates. Our parameters will be r and theta. You can see that z will be 9 minus r squared. X will be r cosine theta, the usual translation between cylindrical and rectangular for the x coordinate. Y will be r sine theta, and z will be 9 minus r squared. The tangent vectors will be tr and t theta. Tr will be cosine theta, sine theta, minus 2r. T theta will be minus r sine theta, r cosine theta, and 0. TR cross T theta will be 2r squared cosine theta minus, 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 4 minuses, 2r squared sine theta, and then we'll use a Pythagorean identity here. R cosine squared theta minus a negative is plus r sine squared theta. That reduces to r. Note that we can factor an r out of each coordinate, and that will simplify the calculation of the norm. The element of surface area will be the norm of TR cross T theta, dr d theta. And r will come out of the norm. We'll have the square root of 4r squared cosine squared plus 4r squared sine squared. That's 4r squared plus 1. The surface area then will be this integral. Oops, forgot the dr and the d theta. We'll have r square root 4r squared plus 1 dr d theta. Theta will go from 0 to 2 pi. R will go from 0 to 3. We will, of course, get a 2 pi for free, but name the method for the integration here. Seems that u is going to be 4r squared plus 1, so that du is 8r dr. We don't have the 8s, we'll divide the 8 off. We'll have 2 pi over 8. If r is equal to 0, then u is equal to 1. And if r is equal to 3, 3 squared is 9 times 4 is 36, plus 1 is 37. The r dr will go away, become a du. We'll get u to the 1/2 du. We can cancel the 2 and have pi over 4 out front. Integrating, we have pi over 4, u to the 3/2 times 2/3, evaluated from 1 to 37. This gives us pi over 6, and remember that if you have a to the 3/2, that's a root a. We'll have 37 root 37 minus 1. That is the surface area. Let's calculate a surface area that you can find by other means. In particular, let's calculate the surface area of a torus. To find this surface area, we'll take little cross sections. The cross section will have some radius r, and those will be swept around some bigger radius, big R. If you take a circle and sweep it around like that, the surface area that you get will be the circumference around, for the small circle, times the circumference around the big circle. How far you transport the centroid of that first disk. So the surface area should be the distance around the small circle, that's 2 pi r, times the distance around the big circle, which is 2 pi big R. That's 4 pi squared little r big R. Now let's calculate this using other means. This was by the theorem of Pappus. Our first step will be to find a parametrization. Let's put the center of the small circle on the xz plane initially. And let's measure positions on that circle using a parameter phi. We'll sweep those around through angles theta, making other little circles, and we'll describe positions along that, again by the phi. If we assume theta is equal to 0 initially, then we can calculate x and z as follows. X will be big R, we go big R out, plus little r times cosine phi. It'll be at a maximum when phi is 0. By the time phi gets to pi over 2, you're just at big R on the x coordinates. And y is 0 in this case, z will be r sine phi. Now we'll generalize that by swinging this around, making a torus. In general, x is going to be this value. It's at the maximum when theta is 0. If theta is pi over 2, x is going to be 0. So you end up with cosine theta multiplied onto x. Y is going to be the same thing, but multiplied by sine theta. It'll be 0 when theta is 0, and a maximum when theta is pi over 2. And z will be r sine phi. Here we will assume that both little r and big R are constants, and the parameters are phi and theta. Our parameterization will be just this. Big R plus little r cosine phi cosine theta. Big R plus little r cosine phi sine theta, followed by r sine phi. Calculating the tangent vectors, we'll have t phi, taking the derivative with respect to phi, we'll have minus r sine phi cosine theta, and then minus r sine phi sine theta, followed by r cosine phi. T theta will be minus the quantity big R plus little r cosine phi sine theta, and then big R plus little r cosine phi cosine theta, and of course the last coordinate is 0 because it doesn't contain any thetas. T phi cross t theta can be found in the usual fashion. There is a little trick that we might employ here. We have an r that can be factored out. And on the second one, we have big R plus little r cosine phi that can be factored out. Scalars can be factored out of cross products. It follows then that the cross product will be little r, big R plus little r cosine phi, and what's left over will have a minus cosine theta cosine phi. Minus a negative, and flip the sign on the middle cofactor, we get 3 negatives, so it's negative sine theta cosine phi. And then finally, using the Pythagorean identity again, we'll have a cosine squared sine phi with a minus, minus a negative and a negative, 3 negatives, will be minus sine phi sine squared theta. We end up with minus sine phi, accounting for the Pythagorean identity. To calculate then the surface element, that is of course the norm of t phi cross t theta, d phi d theta, and that will be little r, big R plus r cosine phi, and then the norm of what's left over, square root of cosine squared theta cosine squared phi plus sine squared theta cosine squared phi plus sine squared phi. Combining them 2 at a time, the radical ends up giving us 1. And then we multiply by d phi d theta. The surface area then will be calculated by integrating the surface element, r times big R plus R cosine phi, d phi, d theta. Theta will go from 0 to 2 pi, and phi. Phi goes from 0 to 2 pi as well this time. As you can see, there are no thetas, so we do get a 2 pi for free. When we integrate cosine phi from 0 to 2 pi, we get nothing. So what remains is the constant little r times big R integrated from 0 to 2 pi. We just multiply by the 2 pi. That gives us 4 pi squared little r big R, the same as from the theorem of Pappus. Don't you just love that theorem of Pappus? Yep, we're very happy because after all these computations, we were able to derive something that was trivial by the theorem of Pappus. At least we know that the theory that we have developed is able to reproduce other results. We now know how to calculate surface areas, but surface integrals are integrals over some surface of a function up against a surface element. These are always going to be double integrals. You may also write them as integrals like this. If the surface is a closed surface, like a sphere, then you can also put a little embellishment on these, a little circle around those integrals, indicating you're integrating over an entire closed surface. For the purposes of our integral theorems, we will need to know that our surfaces are orientable. So I need to define what I mean by that. It is called orientable if it has a continuous unit normal field. For example, a sphere is orientable because you can continuously assign a unit normal field all across the surface of the sphere. A plane is orientable. A hyperboloid of one sheet is orientable. Let me show you an example of a surface that is not orientable. It's called a Möbius strip. I'm going to make it from a sheet of paper. I'm going to tear off a little tab. Let's see. I'm going to fold this lengthwise. We're just going to tear off a little strip. We'll fold it back and forth a couple times. And that will make it so that we can tear the fibers lengthwise, like that. I have this sheet and I'm going to take it and twist. And then I'm going to staple the edges together. So this is a Mobius strip, or sometimes referred to as a Mobius band. Now, let's suppose that we have a creature that lives on this surface as this creature's entire universe. This creature's name is a square. Now, we're going to presume that a square does not live on the surface. He doesn't live on one side or the other. Suppose that a square lives between the layers of the surface. He's able to move around between the layers. So he's not living on one side or the other. He's living in the surface. And let's suppose that he's a happy sort. And he's going to commit a global act of graffiti. Here he is. But if he were able to stick something out of the surface, it would form a normal field. Let's suppose a unit normal field that could stick out of the surface. If we were to take that unit normal field and transport it around until we got back to where he was, the normal field would now be poking out on the other side of the surface. And that means you could not continue this around in a continuous fashion. It would be poking around like this as we go this way, and as we come back, it's on the other side. We cannot continuously assign this in a nice, smooth fashion. And a square can discover this. As he goes around his universe, making this global act of graffiti, going in this direction and holding out his left arm, he continues to deface his universe. His hand is always in contact with the left edge of his universe. Now a square is moving around, and he continues this global act of graffiti, making a mess of everything. And perhaps you can see that when he gets back to where he started, what used to be his left arm has become his right arm. He's now touching the other side, even though his hand was in constant contact with the left side of his universe as he went around. When he came back, his hand was now touching the opposite side of the universe. It's as though a square went on a vacation away from home, far from home, and when he came back, the sides of his body had switched. That is why this surface is not orientable. The definition for an orientable surface that we have given here, the ability to continuously assign a unit normal field, is not very satisfying because it is extrinsic. A property is extrinsic if you have to appeal to something outside of this space. Surely, a square should be able to discover, without having things poking out of his universe, that his space is not orientable. There should be an intrinsic definition of orientability that will take the place of our intrinsic one. In fact, the intrinsic definition is almost built into the way we've drawn a square. He's moving in one direction and holding out his left arm. He's forming what is called a frame field. A frame field has right angles and unit vectors. If you can continuously assign two vector fields at right angles to each other at each point around the surface, then if every time you transport this around a closed loop, you end up at the same place, and if you can continuously assign that frame field around all closed loops in the surface, then the surface should be orientable. But if you have a path, one path, for which that frame field is not continuous, then it's non-orientable. Because we were assigning frame fields pointing left and up, all the way around, and when we got back to where we started, we were still going up, but instead of going left, we were going right. That's a non-continuous assignment of that frame field as we went around that closed loop. That's only possible because this surface is not orientable. There are other non-orientable surfaces you should be aware of. In particular, there's the famous Klein bottle. A Klein bottle is a surface like this. As you can see, I've graphed this Klein bottle. It is a non-orientable surface, but it really only exists in 4 dimensions and not 3 spatial dimensions. If you have this in 4 dimensions, it's possible that this little piece in the back here can take the 4-dimensional elevator and bypass this surface, go inside, and then come out through the base. You can see that as you go around here along the stem, you can come back in. When you pop back out, your orientation reverses. What used to be your right is now your left, and what used to be your left is now your right. So if our universe had any structures like this, you could go on vacation and come back with the sides of your body reversed. In order to read all of your books or street signs or whatever, you'd have to go on the trip again. There's a guy out in Oakland, California, who makes these things at the Acme Klein Bottle Company. You can buy these things from him. He makes them out of glass. He blows the glass and fuses the pieces together to form a Klein bottle. And this part on the stem where it intersects the other surface in 4 dimensions wouldn't intersect at all. And so this it's kind of genius what this guy does. He makes these Klein bottles, and including a Klein stein or a Klein cask. He also makes Mobius scarves, if you want to check out his site. Let's evaluate the integral on S of x plus z ds, where the surface S is the first octant part of y squared plus z squared equals 9, and 0 is less than or equal to x is less than or equal to 4. Y squared plus z squared equals 9 is a cylinder. And we'll draw the circle of radius 3 in the YZ plane, but drag that along the x-axis until we get to 4. So this will be our surface. We're integrating on that surface the function x plus z. X's and z's are all positive, so both terms should give us a positive component to the answer. Our answer must be positive. Y squared plus z squared equals 9 is easy enough to parameterize. Y equals 3 cosine theta, z equals 3 sine theta, but this leaves x unconstrained. So our surface parameterization will depend upon x and theta. It will be given by x equals x, y equals 3 cosine theta, z equals 3 sine theta. To calculate the surface element, we need to evaluate tx, well that's easy, 1, 0, 0, and t theta, which is 0 minus 3 sine, 3 cosine. Tx cross t theta is 0, followed by 3c, but we put a minus on that cofactor, and then a minus 3s. The surface element will be the norm. You can see the 3 comes out, the negative 2 in absolute value. We'll have 3 times the square root of cosine squared plus sine squared, which is 1, dx d theta. We have then, for our surface integral, the integrand x plus z. Z was 3 sine theta, and then ds, which is 3 dx d theta. X goes from 0 to 4. Theta goes from 0 to pi over 2. Integrating with respect to x first, you can bring this 3 out. We'll have x squared over 2 plus 3x sine theta, evaluated from 0 to 4, d theta. We'll have 16 divided by 2 is 8, plus 12 sine theta minus 0, d theta. Integrating, we have 3 times the constant 8 times its interval length, pi over 2, plus 12 times the interval of sine from 0 to pi over 2. That's half a bump. Half a bump gives you 1. We can factor a 4 out. That'll give us 12 times pi plus 3. On the next problem, suppose we have the surface x squared plus y squared equals z squared. Do you know what kind of surface this is? That's an elliptic cone. Let's choose z values between 0 and 4 so that we just have a piece of the upper nap of the cone. And let's also suppose that we have a density distribution just on the surface. A surface density, much like we might have, say, electric charge, which builds up on the surface of objects. We have a surface density for those electric charges, measured perhaps in coulombs per square meter. Let's suppose that the density is 3 times z, which means the density becomes greater and greater as we go up, kind of the opposite the way electric charges would. Charges would gather at sharp points like this. But suppose that rho is 3z. Then the total mass, if this is, say, kilograms per square meter, the total mass would be to integrate on the surface that surface density times the element of surface area. If the density has units of kilograms per square meter, and the element of surface area has units of square meters, when we add this up over the surface, we'll end up with units of kilograms, the total mass. To calculate that, we need to have a surface parameterization. Note that z squared equals r squared in cylindrical coordinates, which it makes sense to use because of the rotational symmetry of this object around the z-axis. For positive values of z and positive values of r, that gives us z equals r. Using our cylindrical coordinates for parameterizations, z will not be one of our parameters, r and theta will. The parameterization will be r cosine theta, r sine theta, and then z is equal to r. Tr is going to be cosine sine 1. T theta will be minus r sine, r cosine 0. Tr cross t theta will be minus r cosine. We subtract a negative and then switch the sign, that's 3 negatives, r sine, and then r cosine squared plus r sine squared simplifies to just r using the Pythagorean identity. We can factor the radius r out, leaving a 1 in the last coordinate. That'll make it easier to calculate the norm. The element of surface area then will be the norm. R will come out. We have cosine squared plus sine squared, which is 1, plus 1, all under a square root, dr d theta. The total mass then will be the integral of the density. The density we said was 3z. Remember, we'll evaluate this on the surface, and on the surface z was equal to r. Then we'll have r root 2 dr d theta. Theta will go, of course, from 0 to 2 pi, and z goes from 0 to 4, and that means r goes from 0 to 4 since z equals r on the surface. We get 2 pi for free. The 3 root 2 comes out. We have r squared. That gives us r cubed over 3, evaluated from 0 to 4. 4 cubed is 64 times 2 is 128. 128 root 2 pi minus 0, and that is the total mass. There are a couple other ways of calculating the surface element that I would like you to be aware of. In particular, if we have z expressed as a function of x and y, there's a special formula then that we could use for that surface element. We can save ourselves a lot of time. You can see that the tangent vector tx will be 1, 0, fx, and ty will be 0, 1, fy. Tx cross ty then is minus fx minus fy because of the negative on that cofactor, and then positive 1. The surface element then will be calculated with the norm. That's the square root of 1 plus fx squared plus fy squared, all times dx dy. This is the formula you need to know. It will speed things up a little bit in some cases. Here's a quick example. Suppose our surface is given by z equals 4 minus x squared minus y squared. This is an elliptic paraboloid peaking at a height of 4, opening down, intersecting the xy plane in a circle of radius 2. Let's take the portion above the xy plane. Now, how do we calculate the surface area? The surface area is the integral over the surface of the surface element. The surface element is pretty easy to calculate because it's the square root of 1 plus the derivative with respect to x squared plus the derivative with respect to y squared dx dy, which simplifies as 1 plus 4 x squared plus y squared, which we'll look at as r squared. Projecting down into the domain of parameters, which will be the x's and y's below the surface, or r's and theta if we so choose, it looks like we should choose polar coordinates in the xy plane for the domain of parameters, in which case we replace dx dy by r dr d theta. The surface area is then the integral as theta goes from 0 to 2 pi all the way around, and then as r goes from 0 to 2, of r square root 1 plus 4r squared dr d theta. This integral is not hard to evaluate since we have an r, the derivative of something lying around, and the integral does not depend upon theta, so we get 2 pi for free. If we set u equal to 1 plus 4r squared, then du will be 8r dr. We'll divide the 8 off. We'll have 2 pi. The integral transforms to the integral from 1 2 squared is 4 times 4 is 16 plus 1 is 17. We'll have a 1/8 u to the 1/2 du. With a little cancellation, we'll have pi over 4 u to the 3/2 times 2/3, evaluated from 1 to 17. That gives us pi over 6 times 17 root 17 minus 1. If our surface is expressed as a level surface, big F equal to 0, there is yet another way to calculate the surface element. In particular, we'll try to go for the element of surface area is the square root of 1 plus dz dx quantity squared plus dz dy quantity squared dx dy, thinking that we can implicitly solve for the derivative of z as a function of x and y. We'll have to do that implicitly, though. You'll recall that implicitly dz dx is minus fx over fz, and dz dy is minus fy over fz. How does that affect our surface element formula? You can see that the surface element will be 1 plus minus fx over fz squared plus minus fy over fz squared dx dy. If we think of 1 as minus fz over fz quantity squared, we can take that fz squared in the denominator and factor it out. We'll end up with fx squared plus fy squared plus fz squared under the radical over the absolute value of fz dx dy. The numerator is the norm of the gradient of f. You can vary this by replacing x and y with, say, x and z, instead dividing by the absolute value of fy. There's something a little unsatisfying about the method for calculating the surface area element that we have given so far. It involves taking a cross product, which gives us something normal to the surface. A square should be able to determine areas of objects within his universe without reference to things that poke out of the universe. In particular, if everything that he uses geometrically involves only tangent vectors to the surface, since tangent vectors can be thought of as velocity vectors for objects moving in the surface, those are intrinsic. Normal vectors are not. They are extrinsic. There is an intrinsic way to calculate the element of surface area. It goes like this. Given a parametrization for the surface, we find the tangent vectors tu and tv. Those are tangent to the surface, so they are intrinsic. We will set GUU to be tu dot tu, GUV to be tu dot tv, and that will be the same as GVU because the dot product is symmetric. And we'll also set GVV to be tv dot tv. We will then set little g to be the product, GUU GVV minus GUV squared. This is the determinant of these entries. GUU, GUV, GVU, GVV. It turns out, I'll make the claim, that the element of surface area is the square root of g du dv. prove this claim, we will want to show that the norm of Tu cross Tv is the square root of g, and we'll do that. There are some advantages to using the square root of g for your surface element. One is that g is intrinsic. You can calculate it only using dot products of tangent vectors. You don't have to have anything poking out of the surface to be able to calculate it. Also, using a cross product requires that the vectors Tu and Tv be in R3. The other method allows the vectors to be in any dimensional space. So you don't have to be constrained to R3. You could be in R2 or R4 or R10, whatever dimensions you want to work in. What is more, the method with the square root of g is generalizable. If you have 3 dimensions, you'll have 3 tangent vectors, Tu, Tv, Tw. You'll end up with a 3 by 3 matrix, and you can end up with, instead of a surface element, you'll get a volume element. And if you're in 4 dimensions, you can get a 4 volume element, etc. So the square root g method is generalizable to higher dimensions, whereas the norm of the cross product method is restricted only to surfaces that are embedded in R3. To prove this claim, let's suppose that Tu has coordinates a, b, c, and Tv has coordinates x, y, and z. Then Tu cross Tv will be the vector bz minus cy, the negative of az minus cx, and then ay minus bx. It follows then that the norm of Tu cross Tv, and let's square this so that we don't have to deal with the square root. Both sides of this equation will have a square root. When you calculate a norm, it involves a square root, and the square root of g obviously has a square root. We'll square both sides and not deal with the square root. This will be bz minus cy quantity squared plus az minus cx quantity squared plus ay minus bx quantity squared. To calculate g, we need to find GUU, which is Tu dot Tu. That's going to be a squared plus b squared plus c squared. GVV will be x squared plus y squared plus z squared. And then GUV will be ax plus by plus cz. The value of g then is going to be a squared plus b squared plus c squared times x squared plus y squared plus z squared minus ax plus by plus cz quantity squared. So the question is this boxed quantity the same as this other boxed quantity? Are they equal? To settle that issue, I'm going to use the computer. What I intend to do is subtract both expressions and see if I get 0. The second expression was of the form quantity times quantity minus quantity squared. The last quantity was a times x plus b times y plus c times z. We also had x squared plus y squared plus z squared. And we had a squared plus b squared plus c squared. The other side was the norm of the cross product. That was of the form coordinate squared plus coordinate squared plus coordinate squared.
The first coordinate was b times z minus c times y. Then we had a times z minus c times x. And then a times y minus b, times x. Now, if what I have asserted is true, if the two forms of the surface element are the same, the norm of Tu cross Tv and the square root of g, if those are really equal, then when I hit enter, we'll get 0. We're subtracting both of those expressions. If they are the same, the difference will be 0. And ta-da! We've proved it. The square root of g does give you the same thing as the norm of Tu cross Tv.
Let's work an old example to see how this works out. Z equals 4 minus x squared minus y squared, z above 0. Our old elliptic paraboloid peaking at 4, intersecting the axis at 2. You'll recall that our parameterization was r cosine theta, r sine theta, and then 4 minus r squared. So the tangent vectors were cosine, sine, negative 2r, and t theta being minus r sine, r cosine, and 0. Now let's calculate GRR, which is the dot product of TR with itself. We'll get cosine squared plus sine squared, that's 1, plus 4r squared. G theta theta will be r squared sine squared plus r squared cosine squared. That's r squared. And gr theta will be the dot product of these two. The last coordinate goes away. We'll get negative r sine cosine and positive r cosine, and that's 0. G then is the product, GRR G theta theta minus GR theta squared. That's going to be r squared times 1 plus 4r squared. It follows then that the surface element will be r times the square root of 1 plus 4r squared, dr d theta, exactly as before. The rest of the computation will go in exactly the same way. The square root g method can be used in differential geometry and general relativity in 2, 3, 4, however many dimensions you want to work, whereas the norm of Tu cross Tv only works for two-dimensional surfaces embedded in three-dimensional spaces. We also need to look at both flux and circulation. It doesn't have to be across a closed surface, it could just be across a piece of surface. We could have a vector field that's going up across. Again, we only look at the normal portion of that vector field. So the flux will be the integral across that piece of surface, f dot, the unit normal vector to the surface, times the element of surface area. There's something special here that will help us save a little bit of time if we pursue this a little bit. The normal vector can be thought of as Tu cross Tv over the norm of Tu cross Tv. We know that Tu cross Tv will be normal to the surface, but won't necessarily be a unit vector. To make it a unit vector, we need to normalize it, divide by the norm. In this case, ds, you'll recall, is the norm of Tu cross Tv du dv. That means whenever we are calculating flux integrals, we can save ourselves a little time. We can integrate on S, the vector field f, but instead of dotting by Tu cross Tv divided by the norm and then multiplying by the norm and the differentials du dv, we'll just dot with Tu cross Tv du dv, and this is how we will calculate flux more generally. That will save us a little bit of time and an extra step or two. As an example, let's find the flux of the vector field F, and let's suppose it just has coordinates x, y, z across the surface given by z equals 9 minus x squared minus y squared and z bigger than or equal to 0. So the surface is just this little piece to a height of 9 and intersecting the xy plane in a circle of radius 3. To calculate the flux, we do need to calculate the tangent vectors, so we need a surface parametrization. We know how to do that by now. It's going to be what? R cosine theta, R sine theta, and then z equals 9 minus r squared. So TR will be cosine sine minus 2r. T theta will be minus r sine, r cosine, and 0. So TR cross T theta is going to be 2r squared cosine minus the product of two negatives, and then flipping the sign gives us 4 negatives, 2r squared sine, and then r cosine squared plus r sine squared is just r. Once we have TR cross T theta, we should evaluate the vector field F on the surface parameterization. In this case, since the x-coordinate of the vector F is x, we'll have r cosine theta, the y-coordinate r sine theta, and the z-coordinate 9 minus r squared. The flux then is the integral on the surface of F dot TR cross T theta dr d theta. You don't write r dr d theta. That's already accounted for in the TR cross T theta. It's just dr d theta, n times the element of surface area, which, by the way, is sometimes denoted by certain authors as d vector s. If you see a d boldface f, they're using n times ds. It is tu cross tv, du dv, whatever u and v are. So in this case, we're integrating. When we do the dot product, it's going to be 2r cubed cosine squared plus 2r cubed sine squared plus r times 9 minus r squared, all times dr d theta. Theta will go from 0 to 2 pi, and r goes from 0 to 3. We'll simplify the integrand a little bit before integrating. The first two terms of the integrand add up to just 2r cubed, but we also have a minus r cubed. So we'll have r cubed plus 9r dr d theta. We get 2 pi for free. Calculating the integral using the fundamental theorem of calculus, we have r to the 4 over 4 plus 9r squared over 2 evaluated from 0 to 3. We can distribute this 2, and we'll have pi times 3 to the power 4 is 81. 3 squared times 9 is 81. Factoring the 81 out, we get 1½ left over, or 3 halves. We end up with 243 pi over 2 as the flux. On our next example, I'm going to suppose that our vector field is an inverse square field. Remember, those may always be expressed in this way. Recall that Coulomb fields are inverse square fields, as are gravitational fields. If you believe in Newton's theory of gravity, they'll be inverse square fields like this. We'll find the flux of an inverse square field across a sphere of radius r. We haven't specified how big that radius is. We're going to find out if it matters. The flux is the integral over the surface of f dot n ds, where n is the unit normal on the surface. This is the integral on the surface of k over the norm of the position vector cubed times r dotted with the normal vector, but the position vector and the normal vector point in the same direction. The normal vector must in fact be the position vector normalized. K is a constant and can be pulled out of the integral. R dot r is the norm of r squared. In the denominator we have the norm of r to the fourth now, times the element of surface area. We can cancel two norm of r's. On the surface, the norm of r is the radius. And so, since the radius is constant, we can pull that out. And now we're just integrating over the surface area element. If you integrate over a surface, just the surface area element, you end up with the surface area of the surface. The surface area of a sphere is 4 pi r squared. As you can see, the amount of flux for an inverse square field through a sphere of radius r does not depend upon the radius r. If the radius is big or small, you get the same amount of flux of that inverse square field through the surface. Some of you may have seen this principle in a physics class, and it's referred to as Gauss's law. It relates to an electric field. The electric field passing through various sized surfaces will have the same flux no matter how big that sphere that surrounds it. It doesn't really even have to be a sphere, as we'll see later on.